Welcome students. I continue here the microwave spectroscopy. Myself Dr. Nikumbh. This video is for education purpose only. No copyright infringement. This copyright belongs to its rightful owner. In our previous lecture, we start the evaluation of a moment of inertia for rigid diatomic molecule from these three basic conditions and evaluate the value of a moment of inertia which relates the effective mass or reduced mass mu and the bond length, which is also considered as the dimension of the particular diatomic molecule. Now this particular moment of inertia is used to evaluate the total energy associated with the rotating molecule. As we know, the internal energy is quantized. Internal energy is the sum of rotational energy, vibrational energy, and electronic energy. So each rotational, vibrational, and electronic energies are also quantized. Quantized means they possess the fixed value. And for rigid diatomic molecule, the rotational energy is evaluated from the quantum mechanics and the value is given by E suffix j equal to j into j plus 1 into h square upon 8 pi square I, where this I that we have seen in our last lecture, moment of inertia evaluated for rigid diatomic molecule as mu into r square, where h is Planck's constant and j is rotational quantum number or rotational energy state, which takes all positive integer values including 0, 1, 2, 3, 4, etc. Now, this particular energy value, E suffix j, itself indicates it is the rotational energy in joules. Rotational energy in joules. Whenever capital E is represented, then the energy is in joules or in the energy unit. But in the spectroscopy, we are not using the energy values in the energy units, but they are used in terms of centimeter inverse. And how the value of centimeter inverse of that of rotational energy is evaluated, that we consider here. So this is considered as epsilon. Epsilon is the rotational energy in centimeter inverse, and it is evaluated by dividing this energy in joules by Planck's constant and velocity of light. So we know the equation of E as a Ej equal to, now divide this by Hc and we rewrite the equation as 1 H get cancelled. So the equation simplifies to H upon 8 pi square I into C and J plus 1. This is remaining as it is. So this is the one multiplying factor. You find here H is Planck's constant, 8 is a number, constant number. Pi is a constant. C is velocity of light. And I is moment of inertia of a given diatomic molecule. If the molecule is known for study, then its masses will remaining same, because it is also assumed here that during rotation the masses will not change, as well as the bond length will not change, and that's why this mu and r is constant, and hence the quantity obtained from mu and r as a mu r square, that is I, is also constant. So this particular term represents a constant term used in the evaluation of a rotational energy in centimeter inverse, and that's why this is termed as a rotational constant. This rotational constant having the unit centimeter inverse. This is the very important number for the given rigid diatomic molecule. Now, we consider here the expression in the simple modified form B J plus 1, where B is h upon 8 pi square IC, and here it is represented as h cross upon 4 pi IC. So what is this h cross? H cross is nothing but h upon 2 pi. So if we replace this h cross by h upon 2 pi, we get the same equation, that is h upon 8 pi square I into C. So in some reference books we find the rotational constant is represented by h cross upon 4 pi IC, while in some books it is h upon 8 pi square IC. Both gives us the same value for the given diatomic molecule known as the rotational constant in centimeter inverse, and can be obtained by dividing the energy by Hc. Now here you will find not energy only E, but it is delta E. Why delta E? Because in any spectroscopic technique there is a transition of the particular molecule from one of the lower energy state to one of the higher energy state. Here in a rotational spectroscopy, the transition from one of the lower rotational energy level to one of the next or lower rotational energy level will be accounted or considered. And that's why difference between the two rotational energy state is considered as a delta E, and hence simple modification in the previous equation is accounted here. So for the transition there is a rule, and that rule will be considered as selection rule. Now okay, from this particular energy expression evaluated in centimeter inverse, we can substitute the value of rotational energy levels or rotational quantum numbers. If we substitute J is equal to 0, so this term disappears. So 0 into anything becomes 0. So when J is equal to 0, we have energy is 0. When J is equal to 1, so here it becomes 1, here it becomes 1 plus 1, it becomes 2. 2 into 1, it is 2, so it is 2b. So for J equal to 1, it is 2b. For J is equal to 2, it becomes 6b. For J is equal to 3, it becomes 12b. For J is equal to 4, it becomes 20b. J is equal to 5, it becomes 30b. J is equal to 6, it becomes 42b, and so on. You can evaluate the value of a rotational energy level for any rotational quantum number. So this is the representation of energy states. Now you will find here the value increases from 0 when the molecules are present in the ground rotational energy state. It possesses 0 rotational energy. It itself indicates that the molecule is stable. It will not rotate because the rotational energy value is 0. Molecule is stable. It will not rotate. It is in the rest position. But when it is present in J is equal to 1 state, it is the non-zero value and molecules start rotating. Means the higher energy states the molecule rotates, while in the ground rotational energy level the molecule is stable and stationary, which do not rotate here. You will find here the separation distance between the lower rotational energy state is smaller, while the separation distance between the higher energy states is greater. In other words, the separation distance go on increasing for higher and higher rotational energy states. Now, we consider here the rule where the rotational transitions are accounted according to the quantum mechanical theory. And the rule for rigid diatomic molecule is considered as a selection rule. Selection rule gives us the very specificity about the transition of the molecules. A molecule has a rotational spectrum only if it has a permanent dipole moment. If it has only the permanent dipole moment, this is the condition. Second condition, from which energy state the transition is allowed. Delta J is equal to plus minus 1. Plus 1 means absorption of light, photon. Photon means E is equal to h nu. And quantum or an Einstein means E is equal to n h nu, where n is Avogadro's number. Minus 1 represents emission of a photon. Plus 1, absorption. Absorption means from one of the lower energy state to the next energy state. Minus 1 means from one of the higher energy state to one of the next lower energy state. Next lower energy state means from 4 to 3 or from 3 to 2. And for plus 1, from 0 to 1 or from 1 to 2 or from 4 to 5. Now, let us consider here how the molecular population is there. The basic understanding is that if we consider the sample of molecules, all the molecules are supposed to present in the lower energy state. And when the microwave radiations are allowed to interact with such a sample of molecules, then the molecule which possesses the permanent dipole moment get excited to 0 to 1. Means energy state 1 becomes populated. Again the transition is possible from 1 to 2, means the higher energy state, they are also equally populated, and hence what we consider here, all the transitions are shown here from one of the lower energy state to one of the next higher energy state for only J is equal to 1 transition here for our sake of basic condition. Okay, sake of simplicity, we consider here delta J is equal to plus 1 here. So see here, when delta J is equal to plus 1 means the molecules get excited from J is equal to 1 to J is equal to, J is equal to 0 to J is equal to 1. From J is equal to 1 to J is equal to 2. From J is equal to 2 to J is equal to 3. And what should be the energy difference? Can be evaluated. Now represent the energy equation for J is equal to 0, means after substituting the J as 0. Represent the energy expression for J is equal to 1, means substitute J as a 1. And the values are, for J is equal to 1, higher energy minus lower energy, 2B minus 0 gives 2B. For 1 to 2 transition, higher energy is 6B minus 2B is 4B. And in general, from any one of the lower energy state to the next higher energy state, means from J to J plus 1. Means obtain the equation for J as we know, B J J plus 1. Obtain the expression for J plus 1 as B J plus 1 into J plus 2. So subtract higher energy minus lower energy. And one can obtain this expression as a general expression. And if we consider the representation, this is a transition which will appear here as a 2B at the 2B distance. Suppose this is 0B. This is 2B. Next to transition gives, and it will appear at 4B. This is 4B, 6B, 8B, 10B. But here, what I considered initially, now assuming initially that all the molecules are present in the ground rotational state, the first rotational state get equally populated, and hence the transition results equal population. But it will not happen so because of the different conditions that we are going to consider thereafter. See here, you will find this is of low height, somewhat higher, maximum height, again decreasing in height, again less intensity. Height means the intensity of a spectral transition. This is more intense and this is less intense. So height gives us the intensity here. So intensity go on increasing and again go on decreasing. It means the intense transition will be observed for 6B, means from 2 to 3. Transition from J is equal to 2 to J is equal to 3. In other words, J is equal to 2, rotational energy state is highly populated rather than J is equal to 0 state, what we have assumed initially. Means first our basic assumption is not correct because such type of nature of the spectra that one could observe. Now you find, assume that this is 0B, then 2B, 4B, 6B, 8B, 10B, 12B, 14B and so on. So the difference between the two successive lines or peaks, is 2B. 4B minus 2B, 2B. 6B minus 4B, 2B. 8B minus 6B, 2B. Means all the lines in the rotational spectra of rigid atomic molecules are equidistant. Means they are separated by the same distance here. And the strip diagram of a rotational spectrum one can show like this: 0B, 2B, 4B, 6B, 8B, 10B, 12B, 14B and so on. And the difference is of 2B. And from this difference, if we obtain the value of 2B, one can evaluate the value of a rotational constant, that is B. And rotational constant values obtained for carbon monoxide molecule, CO, carbon monoxide molecule, is 1.92118 centimeter inverse. That for hydrogen chloride molecule it is 10.593 centimeter inverse. That for hydrogen fluoride it is 20.956 centimeter inverse. You will find this value is more, this value is less, this value is again still less. It means the values of a rotational constant depends upon the atomic masses, and the value of a moment of inertia, because the reduced mass is related towards the moment of inertia, and moment of inertia is inversely proportional to the rotational constant, because B is equal to h upon 8 pi square I into C. So B and I, they are inversely proportional to each other. Okay, now we consider this the simple example of that of HCl molecule. This we get the spectrum. Very fine spectrum that we get. The higher intensity peaks are considered here, accounted, and the separation distance between the two successive lines is measured as a 2b. So 2b is obtained. You can measure this by using your scale also, and this is found to be equal to 21.2 centimeters according to scale. But this is in terms of centimeter inverse, so it becomes 21.2 centimeter inverse. So this is 2b. From the 2b, 21.2, we can evaluate b by dividing it by 2. Just simple. And from this known value of b, b is known, h is known, 8 is known, pi is known, c is known, I can be evaluated. So I of HCl can be found out. Once you know I, once you know bond length, then the atomic masses can be evaluated. Or knowing the moment of inertia and the atomic masses, the bond distance can be evaluated. And it can be shown here. The evaluation of bond distances in the particular graphic here. See, the bond distances are shown. Here the value of B is represented for HCl, and the bond distance is evaluated 1.27 angstroms. Angstroms means 10 to the minus 8 centimeters. 10 to the minus 8 centimeters or 10 to the minus 10 meters. So in this way, the evaluation of bond distances can be done here. Now, how this particular spectroscopic technique is found to be useful for the another evaluation that we consider here, and that is effect of isotope substitution. Effect of isotope substitution. Now here you will find this is the spectra of HCl, rotational spectra of HCl, but this higher peak, intensity peak is that for H35Cl, and lower intensity peak is that for H37Cl. These are the two isotopes of chlorine, 35 and 37. Isotope means the element having same number of protons but mass number is different. Same number of protons means these are the nuclides having the same elements of the same elements, isn't it? Chlorine, chlorine. Number of protons same means atomic number same. Number of protons same means atomic number same. And here 35, here 37. Here mass increases. From 37 is the normal chlorine and 37 is the isotopic substituted chlorine. So H35Cl is normal hydrogen chloride and H37Cl is isotopic substituted hydrogen chloride molecule. So you will find here normal molecule spectra is observed to right hand side and isotopic substituted molecule spectra is observed to the left hand side, which is to the lower wave number side, which appears to the lower wave number side as compared to this. And how it is that one can consider here by using the another example. Suppose CO, carbon monoxide, carbon 12, oxygen 16. Here we isotopically substituted carbon, carbon 13, oxygen 16 itself. So normal molecule having rotational constant Dist and isotopically substituted molecule having rotational constant Dist. Now B single dash, B double dash. One can consider B prime and B double prime. See, isotopically substituted molecule having the rotational constant smaller than this. Why smaller? Because it is observed at the lower wave number side as compared to this. And this can be understood from this diagram. It is very good in understanding. This is the energy level diagram for normal molecule and this is the energy level diagram for isotopically substituted molecule. You will find here the each energy state is slightly lower than the normal energy state in the normal molecule. So see here, the energy state is lowering. Here approximately the same energy state, here slightly lower, here slightly again more, slightly more lowering, slightly more lowering. So the lowering go on increasing for higher and higher rotational transitions or rotational energy levels. And it itself indicates that this energy difference between the energy state go on decreasing, and that's why delta I becomes small. As delta I becomes small, here the value of rotational constant becomes smaller. Now, from this equation, we can write it for the two compounds. One is normal and another is isotopically substituted. Same equation. For B prime, it is represented here. For B double prime, it is represented here. Ratio is taken. H is constant, get cancelled. C is constant, get cancelled. 8 pi square is constant, get cancelled. Only remaining is I double prime upon I prime. What is I? Moment of inertia. Mu into R square. What we have considered? Again we assume here in the isotope substitution, the bond distance will not change. Bond distance will not change because we have assumed initially the spectra for rigid diatomic molecule. Bond distance does not change. Means I is equal to mu into R square. I is equal to mu into R square. So R get cancelled. R square get cancelled. So only what is the difference? Mu double prime upon mu prime. So this particular value that one can obtain, and it is always greater than 1. Higher number divided by lower number greater than 1. So this value is useful to understand what type of differences in the rotational constant magnitudes will be there. If you know the rotational constant value for one of the normal molecule, you can evaluate the rotational constant value for any isotopically substituted molecule by knowing this particular ratio. Now, we try to sum up what we have considered in the rotational spectroscopic technique. Microwave spectroscopy is concerned for the transitions between rotational energy state of molecule, which possesses the permanent dipole moment. The evaluation of a moment of inertia can be obtained in this particular way. The energy levels are represented by using the energy expression for a rigid diatomic molecule, and B is the rotational constant in centimeter inverse. The selection rule that one has to consider here, and then the spacing between the rotational lines in the rotational spectra will be accounted, which is constant and equal to 2b. Also, we can evaluate the effect of bond length and the mass by using the rotational constant value. And also we have considered the effect of isotopic substitution, which gives us the understanding of atomic masses or atomic weights, as well as isotopic abundances which are present in the nature. Now, why this rotational spectroscopy is important? Because it leads us to understand the bond length, atomic masses, isotopic abundances, and at what temperature the spectra will be recorded. Now we sum up here the merits and demerits of a rotational spectra. The molecules which possesses permanent dipole moment are microwave active, and those are only studied for the microwave spectra or rotational spectra. This is the merit. But the molecules which do not possess the permanent dipole moment, like homonuclear diatomic molecules, they do not give the rotational spectra. This is the limitation or disadvantage. Another merit is it is useful to determine internuclear distances for simple molecules, but it is not useful to determine the bond lengths in the linear polyatomic molecules, because the rotational molecule gives us the single moment of inertia, and from single moment of inertia it gives us the single bond length. But in case of linear polyatomic molecules, there are many bonds in that particular molecule. The third merit that we consider here, the spectra is obtained for the substances which exist in the gaseous state or can be converted into gaseous state only. But the molecules which do not present in the gaseous state, or the molecules which do not able to convert in the gaseous state or vapor state, they are not studied for the microwave spectra. Because when the molecules are at lower pressure in the gaseous state, the molecules are freely rotating, and hence the rotational molecule interact with the electrical component from the electromagnetic radiation, which results the microwave spectra. So this is what we consider about the microwave spectra. Now, next time we consider the new and very important spectroscopic technique, and that one is infrared or vibrational or rotational, or in short IR spectroscopic technique. Thank you for your patience.